Okay, so let me just introduce you. Our next speaker is Professor Igor Vlasenko from Institute of Mathematics in Kiev, and the topic of his talk is chain regular and regular components of the wandering set of surface homeomorphisms. Yes, please.
Thank you. My topic is related to the very old classic results of Birkhoff that are related to the wandering set. I recall that if we have a homomorphism of a surface, then we can define naturally wandering and non-wandering points. A wandering point is a point such that it has a neighborhood such that the iterations of this neighborhood forward and backward do not intersect original neighborhood. And in case if we don't have such a neighborhood, that our point is called non-wandering. An example of a non-wandering point is a fixed point, periodic point, limit point, and so on. We will denote the set of wandering points as WF and the set of non-wandering points of F as omega of F. It's classic definitions. I just recall them. And Birkhoff defined a decomposition of wandering set into so-called omega regular components, alpha regular components, and regular components. A point is called omega regular component if we have a neighborhood of non-wandering sets such that and a neighborhood of X such that forward iterations of our neighborhood V is completely contained in that neighborhood U, for any neighborhood U, starting from some n. I'll show an example. A simple dynamical system on a sphere. We have a 4-point non-wandering set, which consists of 2 sinks and 1 source and 1 saddle point. The rest of points are wandering, but we have further subdivision. Blue points, which are stable separatrices, are omega regular, but not alpha regular, but not omega regular, because when we take a small neighborhood of point on a stable separatrice, then its iterations will expand along the unstable separatrix, and for any neighborhood of non-wandering set, we can contain this neighborhood of point X in this for small neighborhoods of non-wandering set, we cannot contain this yellow neighborhood in green neighborhood. Thus, we have that our point, which belongs to the stable separator, is non-omega regular. But in respect to backward iterations, it's regular. We can take small neighborhood and iterations of our neighborhood V here will be contained in this green neighborhood. Thus, we have the composition of wandering set in classes such as alpha regular, omega regular. When a point is both alpha and omega regular, it's called just regular. And if point is not alpha and omega regular, then it's called irregular. This is classic definition by Birkhoff, but it not much used now. So Berhoff studied those sets of alpha regular, omega regular, and regular sets, defined components as connection components of corresponding sets, and he proved interesting theorems about the topology of those connected components. Namely, if we have a periodic component, what means this means the following: if we have connected components of sets of alpha, omega, and regular wandering points, that we can act on those components using f. And under the direction of f, they will be either invariant, it means f from that component is the same component, periodic, it means it returns into itself, and it can be wandering. It means under the direction of f, it never returns. And Berhoff proved that topology of periodic component is following. They can be either disk or ring. And wandering components are also either disk or ring, but if we have a ring, that is special case for a torus. They are classic theorems, and for example, here we have regular component, a set of white points, which is disks. One such regular component is above the if we take a sphere and throw away a saddle point and its separatrices, we have two connected components which are regular components. If we take a sphere and throw away a saddle point and blue stable separatrices, we have two omega regular components. One is upper hemisphere punctured with source sync 1, and the other is down hemisphere without source 2. I will just draw them. We have corresponding omega regular component as ring 1. This point is Pluto and ring 2. And those definitions are very classic, and there are interesting modern theory of Conley, of chain recurrent sets. This theory was introduced by Conley for flows, and it was adapted for discrete dynamical systems by Franks and Harry. I recall the definitions of the theory. We have so-called epsilon chains, which are finite sequences of points, such that in this sequence we can jump no more than epsilon. We have point x, then we act with our homeomorphism. We have f of x, and we jump on epsilon to a neighbor point. Then we also again act with f, and again jump at most epsilon. And we have a chain, a sequence. And we can define a set of reachable points, and we can limit epsilon towards 0, and we can define chain recurrent points. A point is called chain recurrent if it can be if we can return into it with epsilon chains for arbitrarily small epsilon. And we have the composition of our dynamical system with chain recurrent components and chain regular points. Points which is not chain recurrent is called chain regular. And by analog to Berghoff construction, we can define chain regular components as connected components of the set of chain regular points. And similarly, for this example, we have no difference between chain regular components and chain recurrent components. For this example, two omega regular components coincide with corresponding chain regular components. However, in general case, set of non-wandering points and the set of chain recurrent points do not coincide. So what's the difference between regular components and chain regular components? And let's recall that in Conley theory we also have the notion of attractor-repel pairs. We have a strict attracting set if the set open set U has the property that F maps the closure of U into the interior of U. And we have attractor, which is intersection of images of U, and its basin of attraction and repeller. And in Conley theory, we can split chain regular points using attractor-repeller pairs. And as a consequence, our chain regular components also belong to inside of some basin of attraction of some attractor-repel point. And studying this, we have an interesting theorem that, in fact, there are no wandering chain regular components, and any periodic chain regular component is homomorphic to a ring. That it means that compared with classic Berghoff results, when we consider chain regular components, that we don't have a case when such component is a ring. Consider this example. We have a subset of dynamical system which have a length where the boundary is non-wandering set. Internal is wandering set. Dynamic of this wandering component, which is a regular component, we have points which move from point A to point B. According to our theorem, this regular component of wandering set cannot be chain regular component because it does not homomorphic to a ring. It's homomorphic to a disk. This means that this component must belong to chain recurrent set. And indeed, we can build the corresponding chains by moving along the trajectory, then jumping to the boundary, and then jumping through the boundary using small epsilon and returning back to point A and then going back to point X. It means that indeed the internals of such regular component are chain recurrent. And we have nice result that any wandering regular component of the wandering set is chain recurrent. Any periodic regular component of the wandering set such that is homomorphic to the ring also is chain recurrent. That's an interesting topological descriptions about chain regular sets. Thank you for attention.
I would like to thank the speaker for a very, very interesting talk.